minutes.
Sure.
Yeah. Okay. Good evening, everyone. Am I audible?
Hello, ma'am. Good
Yes,
evening.
ma'am. Good
Okay.
evening, ma'am.
Okay, so in today's session, ma'am will be taking the revision session for quiz 2. Kindly note that, so whatever doubts you have on specific assignment questions, please hold on for this session. So that questions, that sort of doubts can be discussed on Friday session. So for particular question doubts, please wait. We will discuss them on Friday session. Okay, on today's session, so whatever ma'am is going to revise, please concentrate on those topics, and in that topic, in that flow, if you have any doubts you can ask, but please refrain from asking specific question doubts. Okay, so kindly,
Understood, ma'am.
yeah, kindly note this. Ma'am, we can start the session now.
Thank you. Thank you, Lavanya. So, good evening, everyone. As Lavanya mentioned, this is only a revision of the concepts that you need to understand for quiz 2. So, the topics that we are going to cover are permutations, combinations, and up to base theorem. Again, I will not be addressing specific questions which could have arisen either in the assignment or otherwise. But at a conceptual level, if you have any clarifications or questions, please feel free to stop me and ask them. Okay, I think that is what we want to make it very clear, that it is not going to address any particular questions that you have had difficulty, either assignment or in a discussion. Okay. So what is the agenda for today? As we mentioned, this is a revision session. So revision session, it is for, are you all able to hear me?
Yes, ma'am.
Yeah. Okay.
Yes.
Ma'am.
Yeah.
Yes, ma'am.
Okay. So the what we are going to start with is we are going to start with again the basic principles of counting. We'll look at permutations and combinations. In particular, I think we need to bring out the distinction as to when you would apply the principles of permutation and when you would apply the principles of combination to address problems. That is what we are going to first do. Then we move on to the basics of probability, where we again revise the concepts of a random experiment. What is a sample space? What is an event? Then we would look at the properties of probability. Then we would introduce what is conditional probability, the Bayes theorem, and finally we will look at probability trees. So this is just the agenda for today. So let's get started. Even before you learn about permutation and combination, we introduce you to what is called the basic proper principles of counting. When we talk about basic principles of counting, we introduced you to two basic principles of counting. One is what we refer to as an addition principle of counting, and the other is what we represented as the multiplication rule of counting. Now, what is the key difference between these two rules? Now, in addition rule, if an action can occur in n1 different ways and another action B can occur in n2 different ways, then the total number of occurrence of A or B. So the key word that you need to understand here and remember here is A or B. Whenever I talk about addition, it is A or B. And whenever I talk about multiplication, the same rule is if an action A can occur in n1 different ways, another action in n2 different ways, the total number of ways of A and B. So what distinguishes between the addition and the multiplication is in the addition we have A or B. In multiplication we have A and B. So addition becomes n1 plus n2, whereas multiplication is n1 into n2. Now, both these rules, what we state for two actions, can be extended to R actions, as if there are R actions where A can occur in N1, B can occur in N2, R can occur in NR, then the total occurrence is N1 plus N2 plus NR. And the same thing would hold good in multiplication, that if there are R actions performed in a sequential order, then the total number of possibilities of all the R of them to occur together is N1 into N2 into NR. As an example, I think let's look at, suppose I have a choice of 3 pants and 2 shirts, and I have to pick up either a shirt or a pant. So I'm specifying either a shirt or a pant. I can choose a pant in 3 ways. I can choose a shirt in 2 ways. So the number of ways I can choose a shirt or a pant is 3 plus 2, which is 5 ways. I can either choose a yellow pant or an orange pant or a green pant or a black shirt or a blue shirt. So there are 5 different ways to do it. On the other hand, if I say that I need to choose a shirt and a pant, with every pant I associate the two options of a shirt. So you can see that I have 3 into 2, which is I can have a yellow and a black, a yellow and a blue, a orange and a black, a orange and a blue, a green and a black, and a green and a blue, giving me 6 possible ways of doing it. Now, why do we care about the addition rule or the multiplication rule? The multiplication rule is what helps us define the notion of a factorial. Now, what is a factorial? The factorial is defined to be the product of the first n positive integers, and it is denoted by n into n minus 1 into n minus 2 up to 1. By convention, the 0 factorial is equal to 1. Now, using this, we actually use the multiplication rule to come up by defining what is called a permutation. Now, the actual definition of a permutation is an ordered arrangement. I repeat, A permutation is an ordered arrangement of all or some of n objects. So what do we mean by ordered arrangement? The order matters. Again, we keep telling that the order matters. And to be more specific, when we talk about permutation, we look at the case where the objects are distinct, repetitions are not allowed. Objects are distinct, repetitions are allowed. Objects are not distinct. How do we go about the permutation? So let's start the first case where I have permutations. I need to permute or I need to have arrangement of R objects from a collection of N objects. And this is what we denote by NPR. So how do I read this NPR? It is the arrangement or permutation of R objects from a collection of N objects. So obviously R is less than or equal to N. So I have R blanks to be filled. The first one can be filled in N positive ways. Now repetitions are not allowed. So if I have filled the first blank has n choices. This one would have n minus 1 choices. This would have n minus 2 choices and so forth. I apply the multiplication rule. So I have n into n minus 1. The rth one would have n minus r plus 1 choices. So the total number of ways I can actually permute or arrange R blanks or R objects from a collection of n objects is given by NPR, which here I have just applied the multiplication rule. Now, if I look at this carefully, this is n into n minus 1 into n minus 2 up to n minus r plus 1. I multiply and divide with n minus r factorial. If I multiply and divide with n minus r factorial, the numerator is n factorial, which we just introduced. The denominator is n minus r factorial, which gives me that this NPR is n factorial by n minus r factorial. So this is the first formula that you use where you are trying to establish the permutation or the total number of R objects from a collection of N. Remember, distinct objects. That is very important. Second thing, I'm not allowing any repetitions. Any questions here? Clarifications? Okay. So the special cases are NP0, that is, there is only one ordered arrangement of 0 objects. NP1, there are n ways of choosing one object from n objects, which is very intuitive and makes sense. NPn is n factorial, that is, I can arrange n distinct objects in n factorial ways. So all of this, you can just see that if r equal to n, NPn equal to n factorial. So this is the first formula wherein I am establishing that the number of possible permutations of R objects from a collection of n distinct objects is given by this formula. Now, what would happen if the objects are distinct but repetitions are allowed? Again, I have n distinct. So what would change in the entire thing? When repetitions were not allowed, the first blank, I could fill up with n. So how many ways can I do the second one? I'm allowing repetitions. How many ways can I do the second one?
N ways.
Pardon?
N ways.
N ways. Third one?
Same N ways.
N ways. Okay. So you see, when I allow repetition, each way, so I have n into n. I have here n into n into n into n r times, which is n to the power r. And you can see that this is what happens. When repetition is allowed, I have n to the power of r is the number of possible permutation of R objects from a collection of N objects. Now, what is the key thing that we need to understand? These N objects are distinct. So, first thing is whenever you're presented with a problem, understand whether it is distinct. whether you're allowing repetition, distinct, repetition is not allowed. When it is distinct and repetitions are not allowed, it is NPR, which is n factorial by n minus r factorial. When it is distinct and repetitions are allowed, is n to the power of r. This is the first thing that we see. Now, the next thing is what happens when the objects are not distinct. So, when the objects are not distinct, that is, suppose I have, for example, data. Okay. So, what is my n here?
4.
4.
4. Now, what is the thing I notice here is 2 of them are of one kind. Okay. So, how many ways can I arrange this data if 2 of them are of one kind? So, if you go back to your lectures, you see that we say that, okay, call it DA1, DA2. So, I can treat, suppose I have all of them distinct. So, how many ways can I arrange this 4 objects?
NPR.
I have 4 objects. So, how many ways can we do this?
4 into 4
NPR.
into 4.
So, the number of permutations of 4 objects? All of them?
Factorial 4.
Pardon?
Divided by 4.
4 factorial divided by 4?
Divided by 2 factorial.
No, 4 factorial divided by repetition. There are 2 A's.
I'm just saying, suppose it was A1 and A2 and they're distinct. How many ways can you do it?
Factorial 4.
Factorial 4. But this, if A1 and A2 are the same, A1, DA1, TA2 is the same as DA2, TA1. So I need to account for all of these repetitions, and that is divided by this P factorial. So I have it as N factorial divided by P factorial. Is that clear as to how we have got this formula?
Yes, ma'am.
Yeah. Now, suppose I have P1 of one kind, P2 of one kind, I can extend the same thing to the numerator remains the same, but the denominator is P1 factorial, P2 factorial, Pk factorial. And you see that this application is when you can see statistics, Mississippi, Copenhagen, all of these, you can see that these are the typical types of things. Is how many ways can you arrange the letters of these words where I have P1 of one kind, P2 of one kind, and P3 of another kind. So the key thing that we here have is the objects are not distinct, and we have repetition of P1 of one kind, P2 of other kind. So I get a n factorial with P1 factorial, P2 factorial, and Pk factorial. Now, all of this, that is when repetitions are not allowed, NPR, repetitions are allowed, n to the power of r, and when it is not distinct, all of them are linear permutations, in a sense that I talked about linear arrangements. That is, if all of them are arranged in a line or in a row, how it is done. But now we go into circular permutation. And here you find the questions that would arise as, if people are sitting in a round table, how many ways can they sit? How is this different from a linear permutation? One thing that we need to know is, if I have A, B, C, D, and I want to know how many ways can I arrange them if they are in a line. How many ways can I do it?
Factorial 4.
It
4
is
24
factorial.
times.
Yes. Okay. Now, suppose I see and I arrange it in a ABCD is the same as BCDA. Would you all agree with me that these two are the same?
Yes.
Yes, ma'am.
Which is the same as again CDAB?
Ma'am, they're moving in a clockwise direction, but the positions are changing, right?
Which positions are changing?
Ma'am, if we
E.
consider A, so now in the next round, the position of A is occupied by B. So like that, they're changing,
But
right?
if I'm talking of it as a circular arrangement,
Yes.
then how would you look at it?
Uh,
Are these two the same or are they
C.
different?
If I may say,
Hmm.
C and D are coming next to each other. In the second case also, C and D are coming next to each other.
That's what
Though
I'm
their
saying. If
places.
I'm looking at it as a circular arrangement, of making people sitting in a round table. Are these the same or are they the different? Forget about the position of the person in a table. But with respect to this, do you think they are the same arrangement or they are different?
They are same arrangement only.
Same arrangement.
Same, ma'am.
Same arrangement.
Would you all agree with it?
Yes, ma'am.
Yes.
Yes, ma'am.
Whereas if I look at it as linear, so this A, B, C, D, okay, the way I have arranged this A, B, C, D, okay, that
And
is
second
going
BCDA.
is the same as BCDA, which is the same. In other words, if I fix a number A, B, C, D, now is this different? Are these two arrangements different in a table?
Yes,
Yes.
ma'am.
Yes, ma'am.
Okay, but these two are
Yes,
same,
ma'am.
Yes, ma'am.
right? So how do I count the number of arrangements in a circular permutation? Okay, so when I look at the circular permutation, there are two things that I need to understand. One is whether the clockwise and anti-clockwise are same or different. So what do we mean by clockwise and anti-clockwise being same or different? Now look at this. Here, if I fix A, B, C, D, and A, B, C, D. Now, what can I say about the clockwise and anti-clockwise in this case? Similarly, ACDB, ACDB, ADBC.
Ma'am, could you please repeat the question?
If I look at this case, okay, look at this. A is here, okay, B is next to A, C is next to this one. This is the clockwise arrangement. Would you all agree?
Yeah.
Now, here, this is the anti-clockwise arrangement. But
Okay.
if you look at the difference in this, B is next to A, C is next to B, D is next to C. B is next to A, C is next to B, D is next to C. Right?
Yeah.
So if the clockwise and anti-clockwise are different, then these two will be considered differently. Would you all agree?
Okay. Yes, ma'am.
Yes, ma'am.
Is that clear?
Yes, ma'am.
Similarly, if you look at this, A to C, C to D, D to B, B to A, the anti-clockwise is A to C, C to D, D to B, B to A. Here I have this, okay? So if the clockwise and anti-clockwise are different, then I want to know in how many ways can I arrange them in a circle, okay? How many ways can I do that? If they are different, how many ways can I do A, B, C, D in a linear way?
4 factorial, 24.
Factorial. Now, if
24.
I fix A, okay, if I fix A, how many ways can if I fix A spot, how many ways can I arrange B, C, D among themselves?
3 factorial.
3 factorial.
So in general, if I have n objects, okay, and I want to see how many ways they can be arranged in a circle, if clockwise and anti-clockwise are different, so how many ways can I arrange them? It would be n minus 1 factorial. Is this clear?
So
Yes,
if
ma'am.
once
Yes,
you
ma'am.
are fixing A, in the
Yeah.
next step, can't we fix B and then arrange the rest A,
It would
D,
be
and
the
C?
same, right? Whatever you choose, whether if I fix B also, okay, the remaining is 3 factorial way, right? Whatever
Yes.
you choose, A was just as an illustration. Fix one, the remaining can be arranged in n minus 1 factorial. Whatever you choose, it could be B, it could be C.
Okay.
Is that clear?
Yeah.
Right?
Thank you.
Okay, so the key thing that we need to notice here is the clockwise and anti-clockwise are different. What would happen if clockwise and anti-clockwise are the same?
We would have divided it with 2.
You divide it with 2.
2.
Okay, so now once we understand it, then we need to know that when would we use the clockwise and when would we use that the clockwise and anti-clockwise are different. For example, when do you think you would apply this formula n minus 1 factorial, and when do you think you will apply the formula n minus 1 factorial by 2?
Ma'am, there was a question in the assignment which was about the necklace.
Let's look at a more general thing. Simple thing.
When they're
Suppose I'm talking about arranging people in a round table, and suppose I'm talking about arranging beads in a necklace. Okay. When would you think clockwise and anti-clockwise are different, and when would you think clockwise and anti-clockwise are same?
Arranging the
For
beads
the
might be different.
What would
beads are same, I guess.
Beads are same,
Beads
people
are
are
I
same.
also
Beads are
think
same.
beats are
Same and
same,
people
but
is equal. While arranging the
table
beads,
is
we want
different.
clockwise and anti-clockwise would be same when you're arranging beads or when you're arranging people?
yes,
Beats.
ma'am. When you are
Beads.
arranging
Yeah,
beads,
same.
When you're arranging beads, suppose I
Arranging
have a
same.
red color,
clockwise will be same.
it would be the
Same.
same. Okay.
Same.
So I think what you need to understand is in the context of the problem, these are the only two main formula you have. Now there are variants or extensions to it. For example, there are questions which will say that A and B do not want to sit together. Let's start with A and B. So again, go back to a linear permutation. Okay. And I say that, okay, here I have 7 people, I need to choose 3 people. How many ways can I do? I need to arrange 3 people.
7p3.
7p3. But then I say 2 people have to be in the team.
It would be combination, right? In the second case.
Pardon?
Combination.
So, no, 2 people have to be in the team. This
Ma'am,
one.
they can make that two people
Ma'am,
in one.
So
No.
ma'am,
it's only
In
considered
most
one.
cases, what you
you
do is
told
out of 7 people, okay, there are 1, 2, 3, 4, 5, 6, 7. If these 2 have to be there, I consider them as one unit. So what would happen is then it will become 1, 2, 3, 4, 5, 6.
okay.
And among these 2, I can arrange in 2 ways, right? So that's why it will become n minus 1 factorial r factorial, and you'll have problems of this kind. Now suppose I say that these 2 people refuse to be together. They refuse to sit next to each other. How would you solve the problem?
We can like
Then,
subtract the
like the
basic
cases
Find
when
out how
they're
many ways I can do it, how many ways these 2 are together. From suppose the number of ways of having 7 people is 7 factorial minus 6 factorial 2 factorial would be the number of ways that both of them would not appear next to each other. Is that clear? So I'm sure you have done problems of these kind. All of them are application of the original problem. So you have, just as we talked about here, we also have problems where 2 people have to sit together. Now you have couples who sit together, couples who don't sit together, 2 colors are together or 2 colors are not together, and problems of that kind which you address. First you need to see whether clockwise and anti-clockwise are different or clockwise and anti-clockwise are the same. Is this clear?
yes.
Yeah. Okay.
Yes, ma'am.
So the
Yes,
next,
ma'am.
yeah. So the
Yes,
key thing is we started with linear. We looked at distinct objects. We looked at distinct objects with repetitions allowed, repetitions not allowed, then non-distinct objects, and then circular permutation. So the key thing in permutation is we are interested in knowing about the arrangement. But there is another thing called the combination. In combination, basically what you're doing is you are choosing our objects. You're not arranging our objects, but you're choosing our objects from n objects. You are combining them and you are saying that the number of, so there, these 3, suppose I'm choosing 3 objects from A, B, C, D, A, B, C, A, C, B, B, C, A, BAC, CAB, and CBA are the same. Even though they are different arrangements, they give rise to the same combination. So that's why each combination gives rise to R factorial arrangements. So I have this NPR. Each combination gives rise to R factorial, which tells me that this N choose R is N factorial, N minus R factorial by R factorial. The whole way we connect the combination and permutation is to understand that each combination of R objects from N objects can give rise to R factorial arrangements. So one combination gives rise to R factorial. So N choose R will give rise to R factorial into N choose R. And this is the total number of arrangements of R factorial. This is my NPR. So this N choose R is N factorial divided by R factorial by N minus R factorial. This is what is giving me the number of possible combinations of R objects from a collection of, again, N distinct objects. Now, again, there is a very useful results, and these are called combinatorial identities. For example, if I'm choosing R objects from N objects, this is equivalent to rejecting N minus R from N objects. Choosing R is equivalent to rejecting the remaining N minus R. Would you all agree with me? Choosing
Yes,
N
sure.
R is the same as rejecting N minus R. So choosing R is N choose R. Rejecting N minus R. So I have N choose R the same as N choose N minus R. Similarly, N choose N is 1. N choose 0 equal to 1. Now this is a very interesting combinatorial identity which says that choosing R objects from N the same as N minus 1 choose R minus 1 plus N minus 1 choose R. Now what is this? N choose R, I have N distinct objects. I'm choosing R from it. Now fix some object. Okay. When I fix some object, that I can split this N choose R to have that object. Okay, let me call it the Rth object, or the Rth object is not present. Would you all agree with me? It is present or not present. Yeah.
Ma'am, can you tell me how can we use beggar's method?
What method?
Beggar's method.
Can you tell me what? I'm not sure what you want to.
Ma'am, first we give away the objects which are necessary. Then
Yes.
we do the choosing of objects.
Yeah, so that's what I'm trying to explain this N choose R. It's N minus 1 choose R minus 1 plus N minus 1 choose
Okay.
R. Okay.
So we are fixing
What is your
one
left
object.
hand side? What is your left hand side here? How would I tell it? It is choosing R objects from N objects.
And yes,
So let me say that I'm choosing 5 objects from 10 objects. Is that clear?
yes, ma'am.
Right. Now suppose I fix one of the objects. Right? So I
Okay.
have 10 objects. Let me call it A, B, C, D, E, F, G, H, I, J. A, B, C, D, E, F, G, H, I, J. 10 objects, right? Let me fix E1. Let me fix E. Okay. I'm choosing 5 from these 10. So here I can say that this E is present in the choice or E is not present
Not present in a choice. Yes.
Would you agree? Right.
Yes.
Now, if E is present in those 5 objects, how many more should I choose? I've already
The
chosen
remaining objects.
How many? I need to choose
4.
5 from 10.
4. Yes, 4.
But how many do I have to choose that?
9 C4.
Because
Nine.
I have already put this E there, right? So
Yes.
that can be done in N choose 4 ways. Is that clear?
Ma'am.
Right? Okay. Now E is not present. If E is not present, again, how many should I choose?
9C5.
5, right?
Yes.
Is that right? And from
Yes.
how many should I choose that E is not present?
Because I have only 9 choices left.
So it will be 9 choose 5. So in
Yes.
general, if the rth is present, I can do it then. So this 9 choose 4 is n minus 1 choose r minus 1. And this is n minus 1 choose r. So that is how this becomes a very important result. Is that clear?
Yes, ma'am, it is clear.
Okay.
I
Ma'am,
had a doubt.
Pardon?
Ma'am, I did not understand this. E is present and E is not present. That is the only thing I'm confused about.
Okay,
Can you
let's
just
do it
elaborate
once
that?
more. I have A, B, C, D, E, F, G, H, I, J. There are 10 objects. Okay, 10 people. Imagine.
Yes.
I need to now choose 5 people from these 10 people.
Yes.
How many ways can I do it?
A 10 P5,
10,
P5.
C, 5.
Yes, sir.
Here is
Yeah.
it clear? Okay. Now what I'm trying to say, pick up anything, either E or F or anything. Suppose I pick up this thing. Okay. Now this 10C5 could include this E or it cannot include this E. E might be a part of this or E might not be a part of it. Would you all agree?
Yes.
Right. If E was a part of it, okay, I've already chosen E. Yes?
Yes.
I've already chosen E. How many more should I choose?
4 more to choose.
4 more. But how many do I have to choose these 4 from?
From 9, because we've already chosen
So
1.
that would be 9 choose 4. That is n choose r is 9, n minus 1 choose r minus 1, 9 choose 4.
Yes.
Right? Now if E is not present, I need to choose how many? E is not there.
Then also we have to choose 5, right?
5.
5
But from how many?
from 9 because we have rejected E.
That would be n minus 1 choose r.
Okay, ma'am. Understood. Thank you.
Is that clear? So that is,
ma'am,
yeah.
ma'am, I have a question.
Yes.
I have memorized the formula in that case, of
Mm.
which you told that choosing odd objects from n objects is equivalent to removing n minus odd objects from total of n objects.
Mm.
So here I want to know that you are telling that we are removing n minus odd objects from n objects, right? So I am not getting it. I think it would be choosing n minus r objects from n objects. So
See,
that's the
no,
confusion
see,
creation.
yeah, see, let's go back to the same thing. I have A, B, C, D, E, F, E, F, G, H, I, J. 10 people, right?
Yes, ma'am. Yes.
So how many ways can I choose 3 people from 10 people?
10C3.
10C3. Okay. If I'm choosing 3, I'm not choosing the remaining 7. How many ways can I not choose 7 people from 10 people?
10C7.
That's precisely what I told. Choosing 3 is equivalent to not choosing the 7, right? So
Okay.
that's why I have n choose r the same as n choose n minus r. This is clear?
Yeah. At first, I thought that since you told that removing
No,
n minus
removing
r
or
objects,
not
yeah.
choosing, rejecting or not choosing. The idea is that, okay, nothing else. Okay.
Oh,
8 people, how many ways can I sit? 8 people. So B and C sit together. E and F sit together, but B and F. See, these are all very specific questions. You can just work it out, and these are the specific questions that you can ask in the discussion forum. This is only at a conceptual level. I think I'll just move forward without taking these specific questions. Okay. So these are important combinatorial formulae. Now, the first thing that I want all of you to be very confident about, and this is where you'll be tested, is many a time we see people having a confusion about whether to apply a permutation formula or whether to apply a combination formula. So from the way the question is phrased, you need to understand whether the order matters or whether the arrangement matters or order does not matter. So let's look at a few typical examples. For example, whenever you are asked to form a password, do you think order matters or order does not matter?
Order
A, B,
Order
matters.
C,
order matters.
So would you use a permutation or would you use a combination?
Permutation.
Very good. Now, suppose you have a pizza parlor which says build your own pizza, or sandwich parlor which says build your own sandwich, and gives you a choice of toppings. Okay, here does the order matter or does it not matter?
Order does not matter.
Does not matter.
Doesn't
So
matter.
You have a combination, so it doesn't matter whether you're putting corn on top of peas or otherwise. So order does not matter, so you'd use a combination. Is that clear?
But
Again,
my question is,
yes.
suppose a person is interested, like his bottom layer should be chocolate, then it should be corn. In that case,
In that case, what would happen? So you
orders
should
matters.
Yes, ma'am.
order matters, right? Order matters in that case. But suppose I'm just giving a choice of this one without even specifying whether the bottom layer should be chocolate and the second should be mayo or something. Their order doesn't matter. I just want a choice of toppings, right? Is it clear? Right.
This is the second thing where I most of the time make mistake.
Yeah. So you need to understand that most of the time where or unless specified that the order matters. Here I'm just giving you a choice of 10 toppings from a list
Can
of.
I say something?
Yeah.
Suppose I get into a shop, I want to buy chocolate for my home. So there are 5 type of chocolate that I'm interested of buying. So in that, will order matter? Because if I'm buying a chocolate, then I would seek the least expensive, the highest expensive. Then on the basis of the price, then I would filter it down. In that case, also order matters.
No, see, that is extraneous information that is given to you. If you have, for example, let me give you, suppose keeping everything is constant, right? And you have to choose 5 chocolates from 10 chocolates. Will it be a permutation or will it be a combination?
You have to choose 5, so combination.
It's a combination, right? Now, suppose I say choose the least expensive chocolates. Then order matters because you're bringing in cost.
Filter it down.
Right. So it depends. So for example, again, that is the thing which team building. From a class of 40 people, you choose 3 people to represent students in a union. Order matters, does not matter.
No.
But if I say from a class of 40 people, choose a president, a vice president, and a secretary, order matters or not, doesn't matter.
Order matters.
Order matters. So the same 40 people, same choosing 3 people, one case order matters, one case order does not matter.
Ma'am.
Is this clear?
Okay. Yeah.
Ma'am, for combination with permutation, you applied condition.
Pardon?
Ma'am, you applied condition to use the permutation with combination. For choosing 3 people out of 40, you applied condition that for vice captain or captain post. So
I said if I have to choose a president, vice president, and secretary, then order definitely matters there. Whereas if I am just choosing 3 students to represent the class, order doesn't matter.
Yes.
Okay,
In that lecture example, you showed me, you showed that A, B, C. Choose them. That A, B, and BA both are equal.
Yeah.
So
AB and BA would be this. Yeah, AB and BA would be the same if I'm just see. There are, for example, if you are looking at heats in a athletic thing, and they are just choosing 3 people from every top 3 from everything goes there. There actually you see that you're choosing the top 3 to get into the next thing, right?
Yes.
Whether you're choosing 3 people, that is how you're doing, right? So you need to be very clear in the context of the problem whether the order matters or does not matter. For example, if you're forming a password, 1, 2, 3, 4 is different from 1, 3, 2, 4. Is it clear?
Order matters, yes, because it
Order matters. So you would always have a permutation there. Okay. Now see, for example, this second problem, if I have a bookshelf with 8 different books, I want to arrange 5 books. How many ways can I arrange? Whenever I say arrange, order matters, but if I
Permutation.
just have to choose 5 books from the 8 books, I just choose. Order does not matter. It would be combination. Okay. So the different bases forming.
Ma'am, may I ask one question?
Yes.
Ma'am, here, what do you mean by, could you please go to the slide?
Yes.
Previous slide. Yeah, I heard you in 4.1 example. Here, I want to know what do you mean by arranging 5 books on the shelves? So, is it meaning the level of the shelves means the
I
down
have only
level
one
from the top
shelf. I
level?
have 8 books, 8 distinct books with me. Okay. I want to just arrange them in a shelf, right? Okay. So if I
Okay.
have call these books 1, 2, 3, 4, 5, 6, 7, 8. So when I arrange them, 1, 2, 3, 4, 5 is different from 1, 2, 3, 5, 4. Would you
Okay.
agree?
Yeah.
Yeah. But
Got
if
it,
I
ma'am.
just
Thanks.
say that choose any 5 books, order
Uh,
doesn't matter. Is
yeah.
that clear? Right?
Yes, ma'am.
That's the thing. Okay.
Thanks.
So as I already said, in team formation, you use a permutation. If I just have to select, if I you use a combination, if I just have to select few people from 10, but if I have to select specific positions, I use a permutation. Is that clear? Okay. Now
Yes, ma'am.
again, 4-letter code forming this is a permutation. Each letter always passwords is a permutation. The key differences that you need to understand is if the order matters, it is a permutation. Order does not matter, it is a combination. Again, n distinct objects are choosing from it NPR. Here it is NGOs. So here what we have established in the first portion as we started with the principle of counting, and I think what you will be tested is on the key difference between permutation and combination. So look at whether the objects are distinct, look at whether repetitions are allowed, look at whether it is a circular with clockwise and anti-clockwise same. If order matters, apply the permutation formula. If order does not matter, apply the combination formula. Is this clear? Any questions, clarifications?
No, ma'am.
Okay.
All good.
Okay, great. Okay, so the next thing that we are going to look at is we are going to review the probability module. Now, why are we learning or why is probability very important for a statistics courses? See, one thing is when you do, even in the statistics course, your first module was basically descriptive statistics, where you were presented the data and from this data you formed tabular summaries, numerical summaries, graphical summaries. You saw the data and from that you created these summaries. Is that clear? That is what you did in your first 4 weeks. Is that right? Yeah. But now what happens is, do we live in a world of certainty or do we live in a world of uncertainty?
Uncertainty.
Uncertainty.
Right. So the minute we go to a world of uncertainty, we understand that we need a tool that would help us actually address this uncertainty. And that tool is what probability tries and gives us. Okay. So once we understand what is the probability and everything, then we actually extend this definition of variable, what numerical and continuous variable that you saw in the descriptive space. We talk about random variables and distribution, but the need for understanding or capturing this uncertainty, we are trying to do it in terms of what we call a random experiment. So first we are setting up what we refer to as building blocks of probability. Okay, just a second, please. So we start with what is called a random experiment. Before even telling what is a random experiment, all of us know what is an experiment. An experiment is a process that produces an observation or an outcome. Very simple. Okay. Now, what is a random experiment? For example, this is an example that I give to everyone. I give each one of you, okay, I just want you to listen to this carefully. I give each one of you exactly 2 glasses, okay? And in these 2 glasses, I ask you to mix 1 teaspoon of sugar, 1 teaspoon of salt in about 50 ml of water. So what is the experiment? Experiment is to mix 1 teaspoon of sugar and 1 teaspoon of salt and 50 ml of water twice. So you have 2 glasses of water. What would be the outcome of this experiment?
A person
Salt
A
and sugar
can
mixed equally.
a
What is the
person
outcome?
A
Yeah.
can either mix salt and sugar in glass 1 or glass 2. There are only two
And you're
chances.
doing the same thing in glass 1 and glass 2. Glass 2 also I'm giving you 1 teaspoon of sugar, 1 teaspoon of salt and 50 ml of water. This is the experiment. Mix 1 teaspoon of salt, 1 teaspoon of sugar and 50 ml of water. Will the outcome be very different if you all were doing the
Same outcome.
experiment in a controlled way?
Same outcome.
Same outcome.
Now I'm giving each one of you one coin or 2 coins which look exactly similar. Two, say, 1 rupee coins. Okay. I'm asking you to toss the coin. Will the outcomes be same or will it be different?
May or may not
Different.
be same.
Different.
May not be same.
Okay.
May or may
What
not
is
be
the
same.
difference between the first experiment and the second experiment?
In first experiment, we know the outcome, but
Second
in
experiment
second
also, you know the outcome. What are the
So
possible
with the
outcomes?
constant variable, the probability might not differ, but with a different variable, probability might differ.
What was the key? Let's bring variable, just in plain thing. What was the key difference between the first and the second? Both the experiments, did you know the outcome?
Yes, but the conclusion is not so strong in the second case.
It is not strong, it is uncertain. Would you all agree?
Yeah,
Uncertain.
yeah.
Right. So that is the key difference. When I talk about a random experiment, the outcome is actually not predictable with certainty. That is my See, this is something which many people say, that in a random experiment, the outcomes are unknown. It is not that the outcomes are unknown. The outcomes are known. When I toss a coin, I know it would be a head or a tail. But what is it that I do not know? I do not know whether the head would appear or tail would appear. There is a outcome is uncertain. Is this clear? The distinction?
Yes, ma'am.
Yes, ma'am.
Yes, yes.
Yes.
Right? So a random experiment is an experiment where the outcome is or it cannot be predictable with uncertainty. Right? So this is the first random experiment, and the collection of all basic outcomes of a random experiment is what we refer to as a sample space. So one of the things is give sample spaces. First of all, tell me what, I'll describe the experiment. Tell me whether it's a random experiment and tell me what is the sample space. I toss a coin 2 times.
Random experiment.
Random experiment.
What would be the outcomes?
Head or tail.
Head or
Two
tail.
times.
Head, tail,
I'm
tail,
tossing
head,
a
tail,
coin 2
tail,
times.
head.
Head.
Head,
Four,
tail.
four,
How many outcomes do I have?
four
I have
outcomes.
4 outcomes. Okay. Right. Now, the next thing I'm saying, I'm leaving from home and I'm reaching my work. I'm noting down the time taken to reach my office from home. Is it a random experiment? What is the outcome I'm tracking here?
How much
The
time did it
time.
take?
Is it a random experiment or is it not a random experiment?
Not a
Not
random.
a random.
Why is it not a random experiment? Do I know how much time I take? Is it certain? Is it uncertain?
Ma'am, I
Uncertain,
think
ma'am.
it would
Certain.
be
Uncertain.
uncertain because you have not mentioned the mode of transport.
Okay,
So
I
it
go by
may
a
be different.
scooter. So do you think that every day if I start from my house in exact 15 minutes, I can reach my work?
No, ma'am, there might be
No.
variations
No.
every day.
So do you think it's a random?
Casually.
So is the outcome known with certainty or is there uncertainty?
Uncertain.
Uncertainty.
Is it a
There
random?
is a some amount of certainty. You can't say like total uncertainty is there, but there is some amount of
But every
certainty
day,
that
but
What would
every
be
day
a
you
sample
cannot
space?
get the same
So the
outcome.
time taken, okay, forget about me reaching from home to this one. Or many of you might be staying in hostels. From your hostel to the department or to your classroom, does it exactly take 10 minutes every day or is there some uncertainty?
Have some
Uncertain.
uncertainty.
So would it be a random experiment in that case?
Yes.
Yes,
Yes.
ma'am.
Yes,
What
ma'am.
is the key difference here? You're tracking time. Is that clear? Yeah.
Yes.
Okay, let me describe another experiment. I keep tossing a coin till I get a head. What are the possible outcomes of this experiment? And describe the sample
unknown.
space.
Head and tail.
I keep tossing a coin till I get a.
It's also
You
uncertain.
can get head at the first toss itself, or else you keep tossing to
Yes.
10 times, then you get a head.
Tail head, tail head, right? So the first sample space you described was HH, HT, TH, TT. Okay. Then I looked at time. I can express this that T is less than or equal to something is less than some 15 minutes or something, right? So you can see that all of them are sample spaces. Would you all agree with me? Yes or no?
Yes.
Now, what is the
Yes.
difference between these two
Yes.
sample spaces? This has finite
One
number
goes
of
on.
outcomes, right? Whereas here I do not know how many outcomes I also have. It could be 4, it could be 5, it could be anything. Would you all agree with me?
Yes, ma'am.
Right?
Yes.
Yes.
Okay. So you can see that the sample space and random experiment are the first building blocks. Now, what is important to us is from here I can define what is called an event of a random experiment. And event is nothing but a subset. For example, again, I define tossing a coin twice. I am interested in the event where a head appears in my first toss. It would be just HH and HT. An event where head appears in my second toss is going to be HH and TH. So these are all subsets of my sample space. So a sample space is a collection of all basic outcomes. An event is a collection of basic outcomes, which is a subset of a sample space. Is this clear? So we started with a random experiment. We introduced what was a sample space and then an event. Now, one of the good things about this sample space and events is the minute I have sample space is a set. If you all know set theory, this is something like the universal set, right? And events are subsets of this universal set. So all the basic the sort of set operations can apply to this. Would you all agree? I can define union of events. I can define intersection of events. What are the basic thing? I can define union. I can define intersection. I can define complement. So again, just what is the sample space here? Tossing two coins, we've already done that. HH,
Headed, tailed, tailhead, headtail.
tail. Head on the first toss, HH, HT. Head on the second toss, HH, TH. Right? Head on the first or second toss,
HHHT.
HH.
TH also.
TH.
TH.
Head on the first and second toss,
HH.
HH. So you can see that this is my sample space. This is my E1. This is E2. Can I express this in terms of E1 and E2?
Even union E2.
It is even union E2. H1, that is head, and this defines even union or, okay, and this defines the intersection even intersection E2. Is it clear? So you can see that this is what we have, even union E2. Whenever I talk about union, it is an OR operator. Whenever I talk about intersection, it is an AND operator. Here is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
One
ma'am.
of the events just as we have a null set, and we also know that the events are subsets of these sample space. I can define what is a null event. A null event is an event without any outcomes, and you can designate it by the Greek alphabet phi. If the intersection of E and F is a null event, that indicates that E and F cannot simultaneously occur. Can I have a head on the first toss and a tail on the first toss?
No, ma'am.
What would suppose I have a tail on the first toss. What are the events?
TH,
TH
TT.
and
TSTT.
ET, right? What is the intersection of head on the first toss and tail on the first toss? It is 5. So I cannot have an event where I have a head on the first toss and tail on the first toss. That would say that this E and F cannot simultaneously occur. So they are referred to as disjoint or mutually exclusive. What we mean by mutually exclusive is the occurrence of one event excludes the occurrence of the other event. So when I talk about outcomes in the simple thing, when I toss a coin, if I get a head, that excludes getting a tail. Would you all agree? So getting head or tail are mutually exclusive events. Is this clear?
Okay.
And they are collectively exhaustive. That is, do I have any other outcome that can happen other than head or tail when I toss a coin?
No.
So you see that the sample space, the way we define the sample space, it's a collection of all basic outcomes which are mutually exclusive and exhaustive. That is, one of the outcomes must occur. Is this conceptually clear what is mutually exclusive and what we mean by exhaustive events? Is this clear at a conceptual level?
If you can give some more real-time example.
Okay. Now, right. Let's go back to this rolling a die. Okay. Let's go to rolling a die. What is the sample space? It's a fair die. Or let me
1,
take a
2, 3.
four-sided die. Every time we talk about a six-sided die. Let me take a four-sided die. What would be my sample space?
1, 2, 3, and 4.
1,
1, 2, 3. I'm rolling this dice twice. How many outcomes will I have?
16.
16.
4 into 4, 16. Okay. Now let me roll a die 1. Let me define an event which is getting an odd outcome. What are the outcomes possible?
1 and 3.
1, 3,
1 and
An
3.
outcome?
5.
5.
Are
5.
they mutually exclusive?
No, ma'am.
Getting an odd outcome and even outcome?
Yes.
yes,
Then
They are
Yes,
Can I
ma'am.
get anything
Yes.
else other than an odd or an even outcome?
No other
No.
possible
No,
outcome.
no.
So it is exhaustive also.
Yeah.
Is this clear as to what
Yes.
is mutually exclusive and what is collectively or what is exhaustiveness?
But, can you repeat the exhaustiveness alone, ma'am?
Can I have any other outcome other than getting an odd or an even?
Any simple example that you can quote in the real time?
Okay, a simple example. Tossing a coin and rolling a die. Okay, let me think here. One second. Cards, I'm not sure how many of you are with cards. Okay, something that in an exam, okay, how many options do you have for an exam? Suppose I have only true or false option.
2 option.
Two
Okay,
options.
two options, right? Suppose
Yes.
you're guessing, right? What are the possible outcomes of this experiment? It will be just
True and false.
Two.
there
True
is
and
no third
false.
option, right? Is that clear? Can an answer be both true and false?
No.
no,
So
No.
are they
No.
mutually exclusive?
No.
Yes.
yeah,
Yes. Yes.
Yes. And do I have any other option other than true or false?
no,
No.
So is there exhaustive outcomes?
yes,
Yes, ma'am.
Is it
Exclusive means if you are choosing one option, then one option is not in the
It cannot
occurrence.
occur. I cannot have an outcome which is both true or false, right? True and
Right.
false, right? So
Right.
only one of them can happen mutually exclusive. I
Got
can
it.
either it would be true or false. Is it
Got
clear?
it. Yeah, yeah.
But
Thank you, ma'am.
it is being
Ma'am, exhaustive
exhaustive is
means
not a necessity. Being exhaustive is not a necessity for being mutually exclusive, right?
No, in a sense, see, when I talk about it as a sample space, right, I am listing all possible outcomes. That is, I'm exhausting. So, what are the possible outcomes in a true or false?
True.
No, what are the
True
possible?
and false.
Both true and false. Do I have a third option or a fourth option? So, I have exhausted all possible outcomes of this experiment. Is it clear? That's
But
what I
if
mean
we
by
have a larger sample space and
you're
there
listing
are
all
two sets,
possible outcomes, right? You're listing all possible outcomes. So you are exhausting all possible outcomes. That's what helps you in coming up with the probability of the sample space. At least one of the outcomes should occur. Is that clear?
yes.
Okay, right. So now the thing is, once I have related the sample space and an event as a subset, I have the set operations. I defined what is union of events. I defined what is intersection of events, what is a null event, what is a disjoint event. All these things already existed in my set algebra. And we know that Venn diagrams is a very powerful way to describe sets. So I do the similar thing when I talk about my events by trying and representing my events using a Venn diagram. Because I already know that this comes from set theory. So you can see that the sample space is the collection of all possible outcomes. That's why I said I have exhausted. There is no outcome that I have not listed in my sample space. I represent it with a large rectangle. This is like the universal set that you have already represented. And all events would be the smaller sets that I am representing. For here example, here I have E and F, which are subsets of my sample space. Are they disjoint or they are not disjoint?
not
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 disjoint.
E and F are not mutually exclusive here. Okay, so the E union F is the entire region, and E intersection F is the blue shaded region. Here you can see they are disjoint sets. Here I can see that.
Can we say if they are disjoint, they are independent?
No. Independent is different from disjoint. Okay. And that is where I'm going to come now. Once we have the probability theory and the probability of sets, disjoint and independence, we'll take examples where they are different. Okay. Right. So now the main thing is having established the sample space and events are subsets of the sample space, I need a probability measure to be associated with these sets. Okay. So the axioms of probability says, the first says for any event, the probability of that event occurring is a number between 0 and 1. That is the first axiom. The second axiom says that the probability of the sample space is 1, which says that the outcome of the experiment will definitely be an element of the sample space. Okay, that's why I'm listing all possible outcomes. So the outcome of the experiment will definitely be an element of the sample space. And the third one is very interesting and important, which says that if I have mutually exclusive events, then the probability of the union is the sum of the probabilities. Now, what we have listed here is the probability of on the left hand side is a countable union of sets. On the right hand side is a summation of the probability. What I'm just going to focus is on a finite union. What do I mean by a finite union? Suppose I have two mutually disjoint events, E1 and E2. What this says is the probability of E1 union E2 is probability of E1 plus probability of E2. This is what the axiom says, that the probability of your union is the sum of the probability provided the sequence is mutually exclusive. Now, what happens? So that is what I'm saying, that the probability of the union of disjoint events is equal to the sum of the probability. Now, what happens is I can derive, using these three axioms, I can derive the probability of a complement. Now, I know that probability of sample space is 1 from my second, this one, axiom. And I also know E union E complement is the sample space. Till here, all of us agree?
Yes, ma'am.
Yes.
Right.
Yes.
And what do I know about probability of the sample space? I know it is 1. What can I say about E and E complement? Are they mutually exclusive?
Yes.
Yes, ma'am.
Yes.
Yes.
Then what would probability
Yes,
of
ma'am.
E union E complement be? It would be probability of E plus probability of E complement, right? But what is this? This is probability of sample space, which is 1, which gives me the relationship that the probability of the complement of any event is 1 minus the probability of that event. And I can similarly show that the probability of the null event is 0. By applying this, I know null is nothing but S complement. I just apply this, probability of S complement is 1 minus probability of S, and I get probability of the null event is 0. Yes, Dasida? Yeah?
Ma'am, I have a doubt, ma'am.
Yes, please.
Ma'am, what does exhaustive mean? Does it mean limited number of options, ma'am?
No, it is, I'm giving all possible outcomes that can be possible. That's what. See, suppose you toss a coin twice. Okay. Will this be my sample space? HH, HT, TH?
Yes, ma'am.
Is this my sample space? I'm tossing a coin twice.
No, ma'am. No, ma'am. No, ma'am.
There is a TT, right? Are there any
Yes,
other
ma'am.
outcomes that can happen?
HH also, ma'am.
I have HH.
Oh, ma'am.
Any other
Yes,
outcome that can happen?
no, ma'am. That's
No.
all, ma'am.
Right. So you see that I have listed all the possible outcomes, and I know that one of these outcomes will definitely happen. That's what I mean. Is that clear?
Yes, ma'am.
So as you said, like
Yeah.
they are disjoint event. So can
Which
we
is
say
disjoint? Which
uh,
is disjoint?
probability of E complement
Yeah.
and
Yes.
that one? So
Yeah.
can we say there are exhaustive? They both are mutually exhaustive, collectively exhaustive.
Yeah. E union E complement will always be S, right?
Yes.
And I know one of S is definitely going to happen. So E
Hmm.
and E complement are mutually exclusive and collectively exhaustive. Yes.
Okay.
Yeah. But if I'm defining E1 to be head in the first toss, HH and HT, right? And E2 to be tail in both the tosses, it is TT. Are E1 and E2 disjoint?
Yes.
Are they exhaustive collectively?
No.
They are not disjoint because in the
Yeah,
second toss you are getting head
no.
till.
E1 and E2. E1 is head in the first toss. E2
Hmm.
is tail in both the tosses. Are E1 and E2 disjoint?
I would
Yes.
say no.
Yes, they are disjoint.
Why would you say they are not disjoint?
Because in
Is
the
there an
even
outcome which is
event,
common to both?
yeah, that is
Which
okay.
one?
I'm saying that as you got head and
Hmm.
also head tail,
Hmm.
which satisfies those condition that you are getting head in the first toss, but
Yes.
also you are getting in the head tail in the second toss.
My E2 was getting tail in both the tosses.
Hmm.
So are
Okay, no,
even,
no, no. Then it's not
but are
satisfying.
they exhaustive collectively? Even
No.
and E2.
No, ma'am.
Yes.
No, I have a TH, right?
Yeah.
Okay. Yes.
So
Yes.
Is that clear?
Yes. Yes.
being collectively exhaustive is not a condition for being disjoint.
Means no sample space elements are left.
Yes, right. But E and E complement will always be collectively exhaustive.
Got it.
Is it clear?
Perfect. Perfectly got it.
Right. Okay. Right. So now there is a very important rule which is called the additive rule. We know that from the third axiom for disjoint events or mutually exclusive events, probability E1 union E2 is the sum of the probability. But what would happen if my events are of this kind? They are not exclusive, E1 and E2. So I can do one thing. I can write this E1 union E2 as A, B, and C. Would you all agree that I can write E1 union E2 as A union B union C?
Yes, ma'am.
Right?
Yes, sir.
So
Yeah.
probability of E1 union E2 would be the same as probability of A union B union C.
Yes.
But are A, B, and C disjoint?
No.
No,
Yes, ma'am.
A is this region.
Yes,
B
yes.
is this region.
Oh,
C,
yeah. But
right? So what would
but A is meeting with B. No, no, no. Yeah,
Not
that
disjoint.
is it.
I can write it this way, right? I can put this as A, this is B, and this is.
Okay, so they are disjoint.
So what would then, if I apply this formula, what would A union B union C be for disjoint sets?
A plus B
Means
plus C.
PA plus PB plus
probability of A plus probability of B plus probability of C.
Now, A can be written as probability of, what is it? This one, A is, so this is probability of
E1.
A plus probability of B. You know, B is nothing but probability of E1 intersection E2. Would you all agree?
Yeah.
Now, probability of A is probability of E1 minus probability of A intersection B. Probability of C is probability of E2 minus probability of A intersection B. Is that right?
Yes,
Yeah.
ma'am.
So I get this would be the same as probability of E1 plus probability of E2 minus probability of E1 intersection E2. This is what we refer to as the addition rule or probability, or generally the addition rule of probability when two events are included. The probability of E1 union E2 is probability of E1
Yeah, ma'am.
probability of E2 minus probability of E1 intersection E2. Now,
Ma'am.
E1 and E2 are
So you have
disjoint,
described it as A, B, C.
which are disjoint, and from there I just got
Okay.
this one.
So,
Again,
ma'am, if they are disjoint, then E1 intersection E2 must be
E1 and E2 are
0.
not disjoint. E1 and E2 are not disjoint. I have written this E1 intersection E2, that this E1 union E2 as three disjoint unions, A, B, and C.
This E1 intersection E2 is came in both.
This, see, for example, what we have done here is the following. See, what we have done here is
So basically, ma'am, in that
I
both.
have this as E1 and this as E2, right? Now, E1 intersection E2 is not disjoint. Agreed?
Yes.
So I
Yes.
cannot apply
Yes.
E1 union E2. Now, this is where I have this shaded region. Okay? And let's try,
Yes.
right? And
Okay. So that intersection region is C, right?
yes,
It
yes.
is okay.
And
It is okay. It is determined as
yeah, so
C.
this one is
That
one.
intersection is C.
Yes. And I have different regions which I have just put. Okay. So one region I have
Okay.
put as this, right? That's what we have done. Is that clear?
Ma'am,
Yes, ma'am.
the derivation I am not able to understand.
Which one?
Derivation.
See, let me do it once more.
No, no, not from the
No.
image, from the mathematical expression.
See, let me tell you that 1 second. See, this is E1, this is C2, right? Now
Yeah.
this area is what I'm calling as A. This area is what I'm calling as B. And this area is what I'm calling as C. Till here, is it clear?
Yeah.
So E1 union E2 is same as A union B union C. Till here, is it clear?
Yeah.
Now, A, B, and C are disjoint.
A, B, yeah.
So probability of A union B union C is probability of A plus probability of B plus probability of C. Till here, is it clear?
Yeah.
Now, can you tell me what is A in terms of E1 and B?
A is basically E1 minus, no, E1, yeah, E1 minus B.
And what is C?
C is E2 minus B.
Okay. So can I write this probability of A as probability of E1 minus probability of B?
Yeah.
Plus probability of B plus probability of E2 minus probability of B. But
Yeah.
B is nothing but E1 intersection E2, right?
Yeah.
So that is how we get our probability. Now, suppose I have 3 events. Okay. Now, what happens is you are excluding and you are including. So you have what is called the property of inclusion and exclusion. Okay, that would, you can extend it to multiple events, but it would not be just, it will be probability of E1 plus probability of E2 plus you're excluding the E1 intersection E2 and you're including the E1 intersection E2 intersection E3. This is E1 intersection E2 intersection E3. Is that clear? And that would be
Yeah.
counted many times. So that is what is called the property of inclusion and exclusion. What we have done here in the class is only to look at 2 events. Is that clear?
Yes, ma'am.
Right?
Yes, ma'am.
So now when I have disjoint events, I know what do I know about E1 intersection E2 if they are disjoint, E1 and E2?
No, E1 and E2 are not disjoint, but
If
A,
they
B,
are
C, which
disjoint, I said
represent
if they
them,
are
they are
disjoint.
disjoint.
If they are
Yes.
disjoint, what do I know about E1 intersection E2?
0.
It's a null set, right? And what do I know about the probability of the null set?
0.
It is
No,
0,
0.
right?
0. 0.
We
Probability
can
of null
see
set
that if they are
0.
disjoint, then probability of the union is, it reduces to
Oh,
the third axiom, right? The sum of the probabilities. Is that clear?
okay.
Yeah.
Yes.
Okay. So this is about the addition rule of probability. So let's look at an application of this rule to understand how it is. Okay, so a customer goes into a clothing store and purchases a shirt with probability 0.3 and purchases a pant with probability 0.2. So what are the events if I have to associate an event? Let S be the event of the customer purchasing a shirt. P denote the event of a customer purchasing a pant. What is probability of S?
Probability of S
Oh,
is 0.3.
0.3.
Probability of P is?
0.2.
P is 0.2.
So let me ask,
0.2.
what event would describe a customer purchasing a shirt or a pant?
P union
P of
S union P.
S
0.5.
union
S
P.
union P, right?
P.
And how would it
Yes.
describe this? This is the chance a customer purchases a shirt or a pant. Is that clear? So is buying a shirt and a pant or is the event, are these events mutually exclusive or do you think they are not mutually? If a person purchases a shirt, does that exclude a person not buying a pant?
No.
No, ma'am, they are independent events. Means they are not dependent on
We have
each other.
not yet come to independence yet.
Okay, okay.
Okay. I'm just asking about disjointness. Are
Yes,
they
it is
mutually exclusive?
disjoint.
Are they mutually exclusive? This is a real-time
Yes.
example you asked.
Yes.
If I buy a shirt,
Yes.
can I buy a
No,
pant?
no.
I cannot buy a pant.
Yeah. Can buy.
Can buy. So they are not disjoint.
Yes.
And what is this? This is the probability of you buying both a shirt and a pant. So what do I know? I know probability of S is 0.3. I know probability of P is 0.2. And I also know probability of S intersection P is 0.1. That's what is given to me. Would you all agree?
Yes, ma'am.
Yes.
Ma'am, I
Yes.
understood
What is
that
the
what you
probability?
told.
What is the
Hello.
probability that I buy either a shirt or a pant?
S
It
union
is
P
P of
complement.
Where
S
S
union P.
Probability S union P.
Ma'am, I have a question.
Yes.
How can you tell that they are not disjoint? I have not understood that point.
If
I
you
have
buy a
understood.
shirt, if you go
What?
to a
Yeah,
shop, if you go to a shop to buy a shirt,
yeah,
okay, right? Does that
yeah.
exclude you from buying a pant? If you buy a shirt, you cannot buy a pant.
No.
You can buy a pant, right?
Yeah.
You can
Yes.
buy both a shirt and a pant.
Yeah.
So, what is mutually exclusive? The occurrence of one event prohibits or excludes the occurrence of the other. Is that clear?
In the term of if let's say the buying shirt be event A and buying pant be event event E2, then event E1 intersection E2 how can it be zero?
It's not zero, it's 0.1 in this.
Okay, so
It's
they
not
are not
zero.
mutual.
So they are not disjoint, right? And it makes
Yeah.
sense, right? Nobody will say
Okay.
that if you buy a shirt, you cannot buy a pant.
Okay.
Agreed? Okay.
Yeah.
So how would I describe the union of these two events? It is either buying a shirt or buying a pant. Would you all agree?
Yes, ma'am.
Now I can apply the addition rule here. This would be 0.3 plus 0.2 minus 0.1, which is 0.4. What is this? This one? This is a probability of either buying a shirt or a pant. But I want neither a shirt nor a pant.
1 minus.
So I'm looking at S union P complement, right? Would you agree? That is what I'm looking at, S union P complement. It's the it's the complement of either a shirt. So that would be 1 minus this, which is 0.6.
0.6.
Is it clear? So this
Yes,
example
ma'am.
just demonstrates that from a real-time example, how you find out what is either, what is and what are, whether it is disjoint, apply the rule of addition probability, and then get what is the probability of neither a shirt nor a pant. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes.
Now, again, when we talk about probability, there is a class of things which are called equally likely events. For example, what do we mean by equally likely? When I toss a coin and I say the coin is a fair coin, the chance of me getting a head is the same as the chance of me getting a tail. Both head and tail are equally likely to happen. Is it clear? I roll a die.
Yes.
I can get any one of these outcomes. It is also equally likely to happen. Okay. But let me give you an example where I have 5 balls, 3 of them are black and 2 of them are blue. The experiment is to pick up one of the balls. Okay. What are the outcomes of this experiment?
Means, ma'am, can you explain how can we say that outcome?
I am having a ball with 3 black and 2 blue balls. Okay.
Yes.
Experiment is to pick up one of the balls. One ball.
Okay.
What are the outcomes of the experiment?
5 now.
What are the
Five
outcomes of this experiment?
one black, two black, three black.
I'm just picking up one ball. I'm just picking up one ball. What are the
Either it is black or it is blue ball
It's either a black ball or a blue ball.
or a blue ball.
Those are the only 2 outcomes, right?
Yes.
Okay.
What is the chance of me picking up a black ball?
Black 3 by
3 by
5.
5. 2 by 5.
Blue ball?
2 by 5.
2 by
Are
5.
they equally likely to happen?
No.
But if there were 3 black and 3 blue balls, are the outcomes changing in the experiment?
Then it will be
Yes.
equal.
No, outcomes are not
No.
changing. Probability.
Are they equally likely?
Yeah.
Yeah.
So is this clear? What are equally likely to happen? So
In 3-3
certain
case, yes, they are equally likely, but when they are like difference in the number of balls, then they are not equally
Yeah.
likely.
So experiments where each outcome in the sample space are equally likely to happen. If the sample space has n outcomes, then it is reasonable for us to assume that they are equally likely. I call these outcomes. Then the probability of any event happening is just that the number of outcomes in that experiment
Ma'am,
divided by the total. Yeah.
ma'am,
Basically,
in
their difference will
Yeah.
be zero
Which difference?
from both the outcome there.
What? No, we are not talking about any difference here, right? What do you mean by differences?
No, for equally likely outcomes, their
Hmm.
difference must be zero.
What difference?
If there are 3 blues and 3 red balls,
No, but
then there is
I can have 3 red balls also. I can have 3 blue, 3 black, 3 blue, and 3 red, and I'm picking up a ball. What is
yeah,
the
yeah.
difference zero here? What do I mean by difference here?
No, for equally likely outcomes there.
Yeah, now I have 3 black, 3 blue, and 3 red balls. What are the outcomes in that experiment?
If we talk about the two events, then
No, what are the outcomes of this experiment? I have 9 balls now. 3 black, 3 blue, and 3 red, and I'm picking up one ball.
yeah, it will be -3.
What were the outcomes of this experiment? I can
Yeah.
either have a
Black, red, and
black,
blue.
blue, or what is the chance of having a black, a blue, or a red?
1/3.
They're equally likely to happen,
Equally
right?
likely.
What is the notion of difference here? Is it clear? So it's just equally likely is if the outcome in the sample space is equally likely to happen. Is that clear?
Yes, ma'am.
Yeah. Okay. Right.
Yes, ma'am.
So one of the typical examples is rolling a dice. Okay. You can define what is the probability of getting an odd outcome or an even outcome by just assuming equally likely outcomes. Okay. Any questions still here?
Ma'am, equally likely, does it mean the probability has to be the same?
Probability of the outcomes are the same.
Ma'am,
Okay.
Suppose I
excuse me, ma'am.
had 3 black, 3 red, and 2 red balls. Okay. Will the outcomes, and I'm picking up one ball. What are the possible outcomes?
Blue, black, and red.
Are they equally likely
so
to happen?
you mean the
Yeah.
chances of
Each
so the
outcome.
No,
yes,
Each
they
outcome
must be
is
same.
equally, then it is called equally likely to happen. Is that clear?
Yes,
Yes.
yes, chances must be equal.
Ma'am,
Right.
is
Like
the
it will fall. Ma'am, you said that in lecture that if rain will fall or rain will not fall,
See that
they are equally likely.
if it is equally likely that rain would fall or rain would not fall, then they are called equally likely. But many a time it depends on the context.
Humidity, yes,
Yeah.
irrespective of factors.
It depends on the context also. Okay, right. Is
Yes.
that okay? Now the next notion or the next concept which is very, very important is the concept of conditional probability. So to understand what is conditional probability, assume I have two events, F and E. I'm interested in understanding what is the probability of E occurring condition that F has already occurred. Okay, let's look at an example here. For example, if I'm looking at HH, HT, TH, and TT, let E be the event that the first toss was a head. What are the outcomes? It is HH and HT. I'm asking what is the chance that F, or let F be the event that the first toss was a head. I'm asking what is the chance that the second toss is also a head, condition that the first toss was a head. So what is happening?
Is half
It would be
HH.
half, right? But how do I understand it? Given already that the first toss is ahead, I want to know what is the chance that the second toss is also ahead. So that is why I'm conditioning it. So you can look at this. I have already conditioned on F. F is this larger circle. I'm interested in knowing what is the chance of E happening conditioned on X. So it would be this fraction, that is this line. And what is the shaded region?
E
Intersection
intersection F,
F
the
to
intersection of
the
events.
total, which is F. So the probability of E conditioned on F happening is probability of E intersection F divided by probability of F, provided probability of F is non-zero. Till here is it clear? This is how we define the
Yes.
conditional probability. Okay. Now, why is this important to us? We use this notion of conditional probability to come up with the notion of independence. But even before independence, just as we had an addition rule, we are going to introduce what is a multiplication rule. So from my definition, I have probability of E conditioned on F is probability of E intersection F into divided by probability of F. So what is probability of E intersection F? I can write
In
it as,
this case, it is P of E. Okay.
right? I can multiply it. Is that clear?
Yes.
Right?
Ma'am,
Yes.
Okay.
ma'am, if we change that P of, suppose you told that P of E by F, then we change that F by E then?
It depends, right? So what is your E and what are you conditioning it on? It depends, right? So let's look at this example through a probability tree thing. Okay, to understand this better. Okay. Now I am going to describe this. I'm tossing a coin twice. Okay. In my first outcome, what are the possible things I can have? If I toss a coin
Head
once,
or tail.
Head or tail.
or tail. Right? Second outcome, it could be either a head or a tail.
Or
So
a
you can
tail.
see that
Yes.
this is my HH, this is my HT, this is my TH, and this is my TT. Till here, is it clear?
Yes, ma'am.
Yes.
What is the probability with which I can get a head in my first outcome? It's a fair
Half.
1 by
1 by 2.
What is this? This is half. What is the probability in the second outcome, me getting a head?
1 by 2.
Half again half.
Okay, so what is the probability of me getting a head in the first and head in the second? That is going to be 1 by 2 into 1 by 2.
1 by 4.
1 by
I
4.
can write it as
1 by
probability
4.
of H1 and probability of H2 given H1. Would you all agree? Probability of getting a head given I had
Yes.
in my first.
Yes,
So
ma'am.
it will be probability of H1 intersection T2 is probability of H1 into probability of T2 given H1. Would you all agree?
Yes.
What would this be then? Probability of T1 intersection H2, which is probability of T1 into probability of H2 given T1. Agreed?
Yes.
And this is probability of T1 intersection T2 is probability of T1 into probability of T2 given T1. Till here, is it all clear? Right. Now, what is
Yes.
the chance of me getting a head in the second toss, given that there was a head in the first toss? It is
It
half.
is half.
What is the
It is
chance of
half, ma'am.
what is the chance of
1
me
by
getting
2.
a head in the second toss, given there was a tail in the first toss?
Half.
It is also half
1
because
by 2.
So does the
yes.
chance of me getting a head in the second toss depend on what was the outcome of my first toss?
Yes, ma'am.
Does it?
No.
No, ma'am. How can
No,
it
no,
depend
no.
on
It
first
does
toss?
not depend, right?
It is not
It is
depend because
independent of
It is
probability
yes.
is
independent, right? Now let's look at another example. Okay, let's look at another example in which instead of tossing a coin, what I'm doing is I'm having a bag, okay, with 4 white and 3 black balls, right? What is the chance? I'm picking up a ball at random. What is the chance of me getting a black ball?
3 by 7.
3 by 7.
3 by
What
7.
is the chance of me getting a white ball?
4 by
4
7.
by
4
7.
by 7.
If you get a black ball, I'm saying go to the second bag, which has 3 white and 6 black balls. If you get a white ball, go to the second bag, which has 4 white and 5 black balls. Okay, this is just as an example. Okay, now pick up another ball at a random. What are the possible outcomes I have here?
It can be
Black
1
or
white.
white.
What is the
So
probability of picking up a black ball here?
6 by 9.
What is the probability of picking up a white ball here?
3 by
3
9.
by 9.
Again, this is also black or white. Probability of picking up a black ball here.
It
4
is 5 by 9. And
And
this
4
is
by
4
9.
by 9.
Does the probability of you picking up a black ball in the second draw depend on whether it was a black or a white ball in the first draw?
Yes.
This is
Yes.
Yes, it depends.
Yes.
So are the
It is
events independent or dependent?
dependent.
Dependent.
Whereas in the first case, you saw that
It was independent.
was independent. Okay. So now, but the multiplication rule actually remains the same. So here, I'm again asking probability of B1 intersection B2 is the even black in the first and black in the second, which is probability of B1 into probability of B2 given B1, which is what? Which is 3 by 7 into 6 by 9. Agreed?
Yes.
Yes, ma'am.
Because
Yes, ma'am.
if bag 1 I got black ball, then only I can choose
B2.
in bag 2.
No, I can also choose in back to, this would be W1 intersection B2, right? What is
Okay, I
this?
got it.
And this is
No, I
probability
mean
of
to say the chances of
chances
6
are going
by
to be
9. That
different,
way.
which is now going to be
Yes.
4 by 7 into
Yes.
5 by 9. But what is the
But if
probability
I
of
want that,
getting a black ball in the second thing? I'm asking what is the probability of you getting a black ball in the second draw? How many ways can that happen?
Five by 9.
adding
upon
both
6.
I can either get a black ball in the second, this one, if it is a black in
or
the
in the
first,
first
or
one.
a white in the first, right? Is that clear?
Yes, yes.
Okay.
We can
So,
add them both.
so now I am bringing in the concept of this generalized multiplication rule, which says that I have the probability of an intersection, which is probability of E1. See, E1 intersection F is probability of F into probability E conditioned on F. This is clear?
Yes,
Okay. So
ma'am.
the next thing is I can extend this to multiple events, and that is called the generalized intersect multiplication rule, which is given by E1 intersection up to N is E1, probability E2 conditioned on E1, E3 conditioned on E1 intersection E2, and so forth. But the important thing is to note from this, okay? This is the multiplication rule.
Ma'am, is there any concept of classical probability here?
Pardon?
For that classical probability?
What is classical probability?
I am asking that is there any concept there?
Yeah, see, you have the frequentist approach, you have the classical approach, and you have what we are referring it to as the axiomatic approach, right? In the axiomatic approach, what we are doing is we are actually coming up with the 3 axioms of probability, and from the 3 axioms of probability, we are getting hold of the probability rules for events. Is that clear?
Okay, ma'am.
Okay. And we are coming up with the rules. Now, why are these rules established? The rules are established for us to come up with probability of events. Now, we already established the addition rule, and we extended that addition rule to not only disjoint event for any 2 events, right? Now, what is the multiplication rule? Through multiplication rule, we are establishing what is called the notion of independence. Now, what is the notion of independence? Just as I said when I talked about disjoint, E union F is probability of E plus probability of F when E and F are disjoint. This comes from a conditional probability definition. Is that clear? Probability of E intersection F is probability of
Yes.
F. Right. Now,
Ma'am,
just
but if my probability, sorry,
yeah, please go ahead.
if my probability, if my probability is not affected by the event,
Yeah.
I can just merely multiply that. You said,
That's all.
you just showed
Suppose
in,
E.
yeah,
What is this E conditioned on F? This is probability of E happening given F has happened, right? But suppose
yes,
this probability of E given F has happened is the same as probability of E. For example, what is the probability of me getting a head in the second toss given there was a head in the first toss?
that doesn't depend on for
Doesn't
head in
depend,
first one.
right? Then what would happen? Probability of E conditioned on F
I
is
just have to merely multiply it. Yes,
so then what happens to this? This just becomes probability of, just as for disjoint events, it was the
F
addition.
into E,
For
P of
intersection,
E.
it's the
Yes,
product. So the multiplication rule, probability of E intersection F is probability of E into probability of F. You say E is independent of F if this happens. Is that clear?
Ma'am, so when we have independent events, it's basically us applying the multiplication rule only, right?
See, if E is independent of F, if probability of the intersection is the product of the probability. Now, when there are two events, it is a if and only if condition. That is, E and F are independent if probability of E intersection F is probability of E into probability of F. If probability of E intersection F is equal to probability E into probability of F, then E and F are into. This holds for two events. When we have three events, it does not have a if and only if. You can go back to the lecture. We have given for three events what is the condition. But what is more important for us to understand is, while we were discussing about disjoint events also, everybody kept asking whether the events are independent or not. So now you see that disjoint and independent are different. Is that clear? The first thing?
Yes, ma'am.
Yes, ma'am.
Right? That is
yes,
the
ma'am.
first concept. And we are talking about probability of disjoint events is the sum of probability. Probability, if they are independent, that is E is independent of F, the probability of the intersection is the product of the probability. Till here, is it clear? Okay. So that is where we come to the next important theorem, which is the Bayes theorem.
Bayes theorem.
Even before, and let's talk about it using an example. Okay. And this is an example. Suppose I have three manufacturing plants, A, B, and C. Okay. It is supplying 20%, 30%, and 50% of all
Excuse me,
the.
ma'am.
Yes.
Ma'am,
Yeah.
is there any more than two events then in that independent?
That's what I said. It is not an if and only if condition. If there are more than two events, you can go back to the lectures. I have given you specific conditions under which it would work. That's where we talk about pairwise independence also. Okay.
Okay.
Yes, ma'am.
Okay.
4 conditions were given in the lecture.
So I just in the paucity of time, I just want to complete the Bayes theorem also. Okay. Is that clear? Right.
Yes, ma'am.
Now, the first thing here, if you understand, if I have three, suppose I'm getting the shock absorbers from three plants. Okay. So imagine I have 100 shock absorbers which come to my factory. I pick up one at random. What is the chance it comes from A?
20 by 100.
It is 0.2, right?
Yes,
What is the chance it comes from B?
0.3.
3.
What is the chance it comes from C?
0.5.
0.5.
Is there any other place which is supplying or everything? If I pick up a absorber, I know it should be either from A or B or C. Would you all agree?
Yes.
Yeah, there some will be one
So
there.
this
Yes.
is collectively, I can say that this is my sample space. What is my experiment? Experiment is I'm picking up a shock absorber and observing from which plant it is coming. I can write probability it's coming from A is 0.2. Probability it's coming from B is 0.3. Probability it's coming from C is 0.5.
0.5.
Till here, is it clear?
Yeah, ma'am.
Is this exhaustive? A, B, and C. If I pick up
Yes,
an
ma'am.
absorber, it should be from one of these three plants.
Yes, ma'am. They are exhausted.
Is it mutually exclusive? Can I have a shock absorber from A
No,
and B
ma'am.
also?
Yes.
Can I have a shock absorber, one shock
How
absorber
can
from
we
both
two?
A and B?
I think it would be not
No, ma'am.
exclusive.
It's
Cannot, right?
not
It
No,
should
mutually
ma'am.
be either
It
from
exclusive.
A or from B or from C.
yes.
Is it clear? Okay.
So they are not mutually exclusive, right?
No, but that's why in the context of the problem, can I have something that can come from both a shock absorber which is both from plant A and plant B?
No.
It cannot,
No,
right?
ma'am, as you are
Yeah.
only picking one.
I'm picking only one. Can that one, so I know that if I'm picking one at random, what is the chance it's from A?
Yeah, 0.2.
It is 0.2.
B, 0.3. What is the chance it's from C?
0.5.
I cannot have this from both A and B, right?
Yeah, correctly. Yes.
Till here, all of
Yes.
us are?
Yeah,
Yes, ma'am,
understood.
got it.
Right. Now, I have in these things, I have a set which I'm going to call the set of defective elements. Okay. This is, what is this? This is the set, this thing is defective. So what is this portion? How would I describe this portion? This portion. How would I describe it? That the shock absorber is defective and it is from A.
Yeah.
How would I describe this portion?
Intersection of
First, it
defective
is,
and
It is
A.
yes,
defective and it is from
and
B.
A.
And this
Yeah.
is, it is
Intersection of
defective.
C and defective from C.
Now, the first thing I want to know is I pick up a shock absorber at random. What is the chance with which it is defective? That is the first question I want to
So
ask. What is the probability
it
that
is,
randomly
yes.
chosen will be defective? Now, what is this D? Would you all agree that I can write this D as D intersection A, union D intersection B, union D intersection C?
Union D intersection C. Yes.
Can I do
Yes.
this? Can I do this? So
Yes.
probability of this is going to be probability of D intersection A, union D intersection B, union D.
Yes.
Can I apply the addition rule now for disjoint sets?
Yes. And
Yes, ma'am.
multiplication for intersection.
Yeah. Okay, so this would be D intersection A plus probability D intersection B plus probability D intersection C. But what is probability D intersection A? Describe that.
It is P of A into P of D after
I said describe it.
D
It
after
is
A.
the chance of you finding
Defective.
a
Defect in
defective
A.
and
Defective
it is
from A.
from A. So
Yeah.
that is the same as chance of me finding a defective given it is from A into probability it is from A.
3 into 0.2.
Yes. Yes,
This will be
ma'am.
Yes,
probability
ma'am.
of D given B into probability of B. This will be probability of D given C into probability of C. Do we know what is probability of D given A? Is that given to me? Records show
Yeah.
that the percentage of defective items produced by A is 3%. So what is this? Probability of me finding a
It is
defective,
probability of, yes,
defective given it is from A, right?
3%.
Right. So this is
Yes.
0.03. What is the probability of A? I already know it's 0.2. This is 0.02 into 0.3 plus 0.01 into 0.5. So I know what is the probability of D. Would you all agree?
Yes, ma'am.
Yes, ma'am.
This
Yes, ma'am.
rule is what we refer to as law of total probability. Is that clear?
Yeah.
Right.
Yes.
Now,
Excuse me, ma'am.
yes.
Ma'am, can you tell me again that how did you find that the probability of getting defective when A is already given? Like,
What is this? Read this. Probability records show that the percentage of defective items produced by A is 3%. What is this? Probability of you finding a defective given it is from A?
it's 3.03. We will divide it by 100.
0.03. That's what I have here, right? I already know probability of A is 0.2.
Okay.
Is that clear? Okay. So this law is what we refer to as law of total probability. Till here, is it clear? What was my initial
Yes.
probability of A? I pick up an item at random. The chance it is from A is 0.2. The chance it's from B is 0.3. The chance it's from C is 0.5. Right? Okay. Now the question is changed a bit. I pick up a shock absorber at random. I notice it is defective. Okay. So what is the
Okay.
information that is given to you? Now I'm saying, what is the probability that it came from A? So what am I asking here? What is the
So if it
information
is
I'm giving
from,
you?
Probability of A given D.
I'm
it is
asking probability of A conditioned on
given that it was defective.
D.
Given that it
right?
was, yes.
Okay.
So it will
Now,
change.
what is from my definition of conditional probability? What is this? This is
It is
probability of
that
A
it is
Probability of
defective.
intersection
A
D
intersection D upon
into
probability of
probability
D.
of D. But I know probability.
Yes.
Again, I know this is probability D given A into probability of A. And I already know
Yes.
this is probability D given A, probability of A, plus probability D given B into probability of B, plus probability D given C into probability of C. Right? From a law of total probability. So this is what is called the Bayes theorem. That is, without having information on whether it was defective or not. Okay, so here we have talked about two mutually exclusive. I can extend it to multiple. A, B, and C, are they mutually exclusive?
No.
Find
Yeah,
out.
A
yeah,
and B
yeah. They
Yes,
are
they
Are
are.
they
mutually exclusive.
exhaustive? Are they
Yes,
exhaustive?
Yes.
yes,
Then
Yes.
the probability of A1 given B, that is probability of a defect A, that it came from A, given it is defective, can be expressed as probability of A intersection D by probability of D. So this A given D is posterior. And why is it posterior? Now I'm giving you, see, initially I said pick up an item and you know what is the chance it's coming from A. Now I'm giving you some extra information. And what is the extra information I'm giving you about that item? It is defective.
item is from A. Item has come from A.
Item is not coming from A. I'm giving you, given it is defective, what is the chance it is coming from A? That is what you are trying to find out.
Okay. It is given that it is defective. That
Defective.
is the
That is
given
extra
information.
information. So you are revising your
Yes.
probability, and that's why it is called posterior probability. And these are what are called prior. What is the prior probability of? Suppose this did not matter, and your posterior and prior were the same, then afterwards, of course, that is a very rare chance, but this is how you work out on conditional probabilities and apply the Bayes theorem. Is this clear?
Yes, ma'am.
Yes.
Okay. So this is
Yes.
about, so the key thing in Bayes theorem is to first identify what are your mutually exclusive and exhaustive events. That is where everybody actually misses out. Okay. So you need to, what are the mutually exclusive and exhaustive events here? Coming from A, B, and C. Is it clear?
Yes.
And what is that event
Yes.
is for that can occur with all of them? It being defective.
Yes.
Is that clear? And then you are applying the first part is
Yes.
law of total probability.
Yes.
The second part is the Bayes theorem. Is it clear? Okay, we have already done the probability.
Yes.
So with this, I think we have just completed. I'll just stop here. There are any questions? I'll be happy to answer. Any questions?
Ma'am, in probability conditional, in probability, I am not able to select that what is favorable outcome or what is my total outcome. Sometimes I am not able to choose that.
See, always I think you should start practicing total outcome. What do you mean by total outcome? Set of all outcomes?
Yes.
Favorable outcome would be when you're defining an event. For example,
Okay.
again, let's go back to tossing a coin. What are the set of all possible outcomes? Tossing
It
a
might
coin
be a
twice.
head or a tail.
Tossing a coin twice.
Yes,
Head,
head, tail, that way.
I'm defining
Yes.
the event where my head appears in the first toss. So what are favorable to this event? HH and HT, right?
Yes.
Okay, so always start with the basics. Start setting up the sample space,
Yes.
and then you define what is a favorable outcome. Is that clear?
Ma'am, because in that
Yeah.
uh
Yes.
that card deck you showed us that there are 4 types of card:
Yeah.
heart, speed. In
Yeah.
that, suppose the question is that the sample space, I know the sum, but sometimes I got stuck that the sum is 7. Now I pick out the things which are adding up to 7. I had a
No, that
sample
is in the
space.
dice. No, I think you're getting confused. That is in the dice. See what
Okay.
this is. I'm rolling a die twice. My entire sample
Yes.
is
Yes.
1, 1, 1, 2, 1, 6.
Still I have to see that the
Six,
sum must
six,
be
right?
7.
So I'm
And
defining
now I
an
am
event. No, then look,
okay.
see, always try and describe the event. Don't look at it only from a
Okay.
mathematical point of view. Suppose the event is getting a sum of 7. Okay. Ask
Okay.
yourself the question, can I get a sum of 7 no matter what was my
Okay.
first draw? Can I get a sum of 7 if my first draw was 1,
Yes, I can get.
2,
Yeah.
Yes.
3,
Yes.
4,
Yes.
Yes.
5,
Yes.
6?
Yes.
Now let me
Yes.
define an event where I'm getting a sum of 8. Can I get a sum of 8?
No, no, no.
Because so
No.
does getting a
When
sum of 7, does
yes.
it depend on what was your first outcome?
No.
Getting a sum of 8, does it depend?
Yes, it depends. What
So
was my
I
first
use this
outcome?
example for
Okay.
telling you
I got
about
it.
dependent events. Is it
Okay.
clear? Okay, that is what we did. Is it clear? So
Yes.
just train yourself to describe the events. Even before you apply the formula, use the formula to validate what you understand intuitively. Is it clear?
Yes, ma'am.
Okay, right. Any more questions?
Ma'am, can I ask you a question, ma'am?
Yes, please.
Yeah, ma'am. In permutation,
Mhm.
we have, if the repetition is allowed, we use the formula n power r.
Mm.
So I usually get confused whether it is n power r or r power n, because the formula is okay, like I know it is n power r, but
Mhm.
when it comes to the question,
Mm.
which is r and which is n, I usually get confused. Can you help me, like give me a tip to
Right. So see,
understand?
the whole idea is, suppose I'm asking you, let's look at, see, again, the context of it all depends on, you should understand what are my discrete, this one,
Mhm.
distinct objects, and what are
Okay.
the, for example, let's look at coming up with a
For
4-digit
password.
password.
Yeah.
Okay. Uh, is it, first of all, tell me how many digits, what is my n here and what is my r here? Assume 0 is not allowed. And
N
only
is equals to 9
number
and
password.
N is equals to 9 and R is equals
9.
to 4.
1 to 9.
So
So
what is
9.
my n? What is my r?
N is
N
1
is
to
equal
9.
to 9 and R is equal to 4.
Would you all agree? Now, how
Yeah.
many, I'm allowing repetitions. How many ways can I fill up the first one?
9
9.
ways.
Second one?
9
9
ways.
ways.
Anyways.
Third one?
9 ways.
So isn't it n to the
Basically,
power of 4?
9
N to
to
the
the
power of
power.
1? Now,
Okay.
suppose I say that repetitions are not allowed.
Okay. Then it
9 into
comes
8 is
9, 8, 7.
9.
Is it?
Yeah.
Now I add the first two are numbers, the second two are alphabets. Repetitions
Then
are not allowed.
uh,
Uh,
Then it will be 9 into 26 into 8 into 7.
Okay.
First two are numbers, second two are alphabets.
Alphabets. Okay.
You get it?
Yeah. Thank you.
So in the context, I always think that don't go and in a hurry apply formula. Understand the problem. Once you understand it, don't you feel that you have a grip of the problem and it's easier to know which formula to apply? Would you all agree?
Yes.
Spend a minute to understand the context of the problem. Is that clear?
Thank you, ma'am. Thank you for the tip.
Thank you, ma'am.
Yeah. Any other questions?
Ma'am, can I ask a question?
Yes, please.
Ma'am, I need to ask, like, what steps should we take in mind while solving the probability and permutation questions? Like, sometimes I get confused in them. Like, how
Keep
to
doing
start?
many problems, ma. You'll get confidence. Okay, just keep doing many things. And I always say, see, spend some time in understanding the context of the problem and then mapping it to the formula that you're going to use. See, what happens is if you're just driven by formula, you lose understanding the problem. So whatever is your, see, for example, I've described it in English. You describe it in whatever language you are comfortable in. You see whether that makes sense to you. All of us have what we call intuition. Okay. So describe the problem. Learn to describe problem in plain language. It could be English, it could be Hindi, it could be Tamil, Telugu, anything that you're comfortable with. And then you start understanding the problem more. Is it clear? Don't be over this one with formula. Because the minute you think that should it be n to the power of r, should be NPR, then you're talking in mathematical language without understanding what you're trying to do. Do you all agree with me?
Yes, ma'am.
Yes, ma'am.
Understand what is required and then apply the formula. Okay?
Okay.
Have an understanding.
Okay, ma'am.
Okay? Right.
Okay.
Thank you, ma'am.
Thank
Thank you for taking your
Thank you
time
all.
out.
Okay, thank you all. Wish you all the best. Wonderful.
Thank you, ma'am.
Right.
Thank
Bye.
you.
Bye.
Same to you.
Thank you, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you all.
Thank you, ma'am.
Thank you.
Thank you, ma'am. I'll take care of the closing the session.
Thank you, ma'am. Bye.